Ingenious foundations. Venice stands on one of the most remarkable foundations ever built. The lagoon's islands were far too soft for heavy structures, so early engineers devised a layered system. Millions of oak and alder piles were driven deep into the mud until they reached compact clay, forming an underground forest. Wooden planks were laid across the piles to spread the weight, and dense Istrian limestone was placed on top, creating a durable building platform. The system's genius lay in its chemistry and geology. Normally, wood decays, but these piles remain permanently submerged and sealed in clay, preventing rot. Over centuries, the timber even mineralized, hardening until it behaved like stone. At the same time, Istrian limestone resisted erosion from salt and water, shielding the base of buildings from constant waves. This combination of stability and resilience transformed marshy islands into solid ground, foundations that still support St. Mark's Basilica and the Rialto Bridge 1,000 years later.
Water-oriented city design. Venice made water its streets. Instead of roads, the city developed around 177 canals and more than 400 bridges, with boats carrying goods while people used narrow alleys and walkways. This separation of transport kept the city free of the congestion common in other medieval centers and gave Venice a major trading advantage. The Grand Canal, over 3 kilometers long, became its central highway, lined with palaces, warehouses, and bustling markets. Buildings were designed to face this watery network. Entrances often opened directly onto canals where families and merchants arrived by boat. Ground floors connected seamlessly to the water with porches for unloading, while upper levels displayed ornate facades meant to impress from the canal. These facades were built as thin stone screens, lightweight yet richly decorated, to avoid overloading the fragile foundations. The result was a city where architecture and transport merged, blurring the boundary between land and sea.
Sacrificial ground floors. Life in Venice has always meant living with the tides. During periods of aqua alta, seasonal surges that raise the lagoon above normal levels, entire streets and squares are submerged. Rather than fortify every building against this inevitability, Venetians adopted a pragmatic strategy, designing ground floors as spaces meant to be lost. These lowest levels were kept plain and functional, often used for storage, workshops, or secondary services. Families reserved the upper floors for daily living where belongings, kitchens, and bedrooms remained safe above the high water mark. As sea levels crept higher over the centuries, many ground floors were simply abandoned, sealed off, or repurposed as cellars. This approach did not fight the water, but accommodated it. By sacrificing the lowest level, the rest of the structure was preserved, creating a model of adaptation that allowed Venice to remain habitable despite constant flooding.
Bridges engineering. Venice was never built on a single piece of land, but on more than 100 small islands. Each was stabilized with wooden piles and stone foundations, then gradually stitched together into a continuous city. At first, people moved between islands by boat or even on horseback through shallow water. Over time, bridges and landfills connected them, creating the dense maze of alleys, courtyards, and canals we see today. Early bridges were wooden or floating pontoons, but these were fragile and temporary. The breakthrough came with permanent stone bridges, the most famous being the Rialto. Completed in the late 16th century, it replaced a series of collapsing wooden predecessors. Engineers drove over 12,000 piles into the canal banks and placed 10,000 tons of stone above to form its arch. More than a crossing, the Rialto housed shops, turning the bridge itself into a bustling marketplace that unified Venice both physically and commercially.
Modern MOSE flood barrier system. Even after centuries of ingenuity, Venice now faces its greatest challenge: rising seas and increasingly frequent floods. To protect the city, engineers created MOSE, Modulo Sperimentale Elettromeccanico, one of the most ambitious flood defense systems ever built. MOSE is made up of 78 giant steel gates anchored to the seabed at the 3 inlets connecting the lagoon to the Adriatic Sea. In normal conditions, the gates lie flat, filled with water. But when tides are forecasted to rise above 110 centimeters, compressed air is pumped in, forcing the gates to rise and temporarily seal the lagoon from the sea. In effect, MOSE can lift a barrier between Venice and the ocean.
Construction began in 2003, and the system became partially operational in 2020. In 2021, it successfully stopped catastrophic flooding at St. Mark's Square, proof that Venice continues to survive through bold engineering.
Flexible, tall design. Venice's buildings were designed to survive on unstable ground through lightness and flexibility. Heavy stone walls would have crushed the wooden piles below, so builders used brick, which was lighter and easier to support. Instead of rigid cement, they used lime mortar, which stays slightly elastic, allowing walls to flex with shifting soil rather than crack apart. Some walls were built in lattice-like patterns for added flexibility, while long iron rods anchored heavy facades and large windows to the foundations, keeping the structures tied together. Because the city could not expand outward, it grew upward. Many houses rose 3 or more stories, tall for the Middle Ages, but lightweight brick kept their weight manageable. Narrow alleys and canals created a dense, compact urban form, with buildings pressed closely together. This combination of flexible methods and vertical growth allowed Venice to thrive for centuries on ground that should never have supported a city.
Rainwater harvesting cisterns. Venice had no rivers, springs, or natural sources of drinking water. Surrounded by salt water, the city faced a survival challenge: how to supply fresh water to its people. The solution was ingenious: rainwater harvesting through public cisterns. Each neighborhood piazza doubled as a water collector. Engineers dug underground basins lined with clay to keep them watertight, then filled them with sand and gravel. Rainfall was channeled from the square's surface into corner drains, filtering naturally through the sand before gathering below. At the center stood a wellhead, both lid and an access point for drawing water. Rooftop gutters also funneled rain into the system, maximizing collection. Over time, Venice built more than 600 cisterns, creating a decentralized water network. This innovation allowed a city surrounded by the sea to thrive entirely on rain, a remarkable achievement of medieval engineering born of necessity.
Tidal sewage flushing system. Managing waste in a city without rivers was one of Venice's toughest problems. Other medieval towns could dump sewage into streams or outside their walls, but Venice sat in the middle of a lagoon with no outlet. The solution was to use the tides themselves as a sanitation system. By the 16th century, engineers built an underground network of tunnels to collect waste from houses and streets. These channels emptied into the canals where the lagoon's twice-daily tides did the work. As the tide went out, liquid waste drained away. When it returned, the rising water flushed the tunnels and carried solid matter toward the sea. The salt water acted as a natural disinfectant, reducing disease compared to stagnant systems elsewhere. Though primitive by modern standards, this tidal flushing network was an ingenious use of nature's rhythms, keeping Venice surprisingly clean and habitable for centuries.